hydraulics, pneumatics, mechatronics, PLC, and electrical. It is a multi-domain software which covers various backgrounds of mechatronics and fluid power. Then we have CNC simulator, which is 100% exact replica of real CNC machine and control panel simulation. You have all the control panels of Fanuc, Fagor, Mitsubishi, Haas, Madak, and various industrial controllers. Then we have Siemens Solid Edge Cam Pro, which is for CAD CAM turning, milling, 3D multi-axis turn mill. We have Witness, which is a process planning and plant layout, factory modeling, simulation optimization software for your various production domains. Then Flownex software, which today we will be showcasing the technical aspects of the software according to the syllabus. Flownex is a thermofluid simulation software for design, modeling, and simulation of systems of like heat transfer, thermodynamics, REC, power plant engineering. Multiple and whole thermal domains can be covered using it. When you have Pro Simulator slash Unisim, which is a power plant and process simulator. Then we have a real arc welding simulator, which is a real arc virtual welding simulation cask for your TIG, MIG, and MMA. All the three major operations of welding can be covered. These were our mechanical portfolio. We have electrical as well. First is NIPLAN for electrical power system and CASPOC for power electronics, machines, and drive simulation. Going forward, we have some of the expert labs, which is ISO standard, industry grade. First is industrial fluid power, all the electro-pneumatic, electro-hydraulic, proportional PID, all the fluid power domains are covered. Then we have mechatronics, automation, robotics, PLCs, DCS, HMI, industrial robotic arm. Then coming to 3, 4, 5, 6, and 7th and 8 electrical as well as power plant domains expert labs can be covered, which you can see in the right side in the picture. Then we have welding turnkey lab, which is dedicated welding lab where the simulator is there and all the machines are there. These are some of our credentials. We have worked in MSME tool rooms with DT and DVT, Maharashtra, Goa, with BOS, Board of Syllabus, then Board of Studies, sorry, then FTA, FCRA, HAL, in MSME Corporate, then TAKIP World Bank, we have given some of our service there. Then I will conclude my company's brief introduction, and I will request Hitesh sir, who is going to showcase Flownex software, to take over the session ahead. Thank you. Hitesh sir?
Hello?
Yes, sir. Please, please, you can take over from here.
I'm audible, no?
Yes, yes, clearly.
Okay. Okay, let me share my screen first.
Yes, yes.
Yeah. My screen is visible?
Yes, sir, your screen is visible. You can start.
Okay. Okay. Good afternoon, all of you. My name is Hitesh Kumar Das. I'm working as application engineer at Dio Research and Engineering Private Limited from last 2 years. Today I am going to present the tool called Flownex and some syllabus as I have shared, you have shared us. First of all, what is Flownex? Flownex is a South African tool developed in 1983. It has both NQA as well as ISO certified tool. NQA means Nuclear Quality Assured Tool. ISO is International Standard of Organization. It has both 1D as well as 2D capability. 1D in the sense of flow parameter, 2D as heat transfer phenomenon. It uses implicit pressure correction to solve the network. What is implicit pressure correction method? First of all, you have to assign boundary condition and input. After assigning of input and boundary condition, it will try to converge mass and momentum. When mass and momentum is conserved, then energy will be conserved. After that, after conservation of mass, momentum as well as energy, it will try to solve the network in steady state. It also solves the network in Navier-Stokes equation. It reduces the time because for creation of network, we use here drag and drop concept. Here no meshing is required as in 3D tools. Next. Some distinguishing features. It has superior modeling capability. You can see we can solve many networks such as gas, steam, and the combined cycle power plant, high temperature gas cooled nuclear power plant, gas and compressed air networks, oil and gas distribution networks, aircraft air conditioning, heat exchanger networks, water and fuel distribution network, ventilation system. It is very user friendly because here GUI is very simple. I will show you afterwards. Here both electrical and DCS library is there, and you can add your own library by using script. What is script? Script is for creation of geometry in a parametric way. Some key technology you can see. It can be used for the simulation of compressible, incompressible, two-phase flow, incondensable, slurry fluid, gas mixtures, various types of heat exchanger, mechanical systems, and other systems. It can be used for both steady state as well as transient capability. Very simple to large complex networks can be simulated here. Models can be rapidly be constructed through drag and drop concept. Here, all the components which are required for simulation are available in master database, and those components are not available. You can create your own component in the project database. Automatic reporting means whatever inputs you are assigning in the file simulation is automatically saved in Excel format. It has advanced visualization capability, means HMI, human machine interface. A non-technical user can easily see and understand the networks. And in HMI also we can control all the parameters. This is the GUI. You can see, first of all, it has got 4 sections. Middle is the canvas. In right, it has 4 sections: component, chart and lookup table, solvers, and snaps. First of all, component. For creation of network, all the components is required is there in component tab. In chart and lookup table, all the curves and charts, curves related to turbine, compressor, everything is there in chart and lookup table. Next, solver. Solver is the heart of the tool. You can see the simulation time, end time, and all in solver. Next, go for snap. Snap, the use of snap is to take the picture of the canvas at a particular instant. Means whatever time you are assigning for the simulation, at what time that parameter is also assigned, and you can go for that parameter by using snap. Next, this is the pan and zoom table, and you can see here top steady state means for steady state option you can go for steady state. For transient you can click on run. This is a pause option. While performing transient simulation, you can pause it means stop it, and this is the deactivate means after running the transient simulation, by clicking on deactivate, it will stop the network at that particular instant. This is all about GUI. Next, what sets Flownex apart from other tools? It has got widest array of combined flow and heat transfer types. All types of heat transfer means conduction, convection, radiation. All types of heat transfers are available here. You can easily integrate with Excel to simulate and do pre and post simulation. You can easily integrate with other tools such as ANSYS Structural, ANSYS Fluent, ANSYS CFX, LabVIEW, WES, MathCAD, OPC, AutoCAD, etc. And you can import your own fluid from NIST and NIST reference probe. Next. These are all our users in India. You can see iGCAR. IGCAR, Indira Gandhi Center for Atomic Research, BHEL EDN Division Bangalore, ISC Bangalore, IIT Madras, IIT Mumbai, IIT Kharagpur, JNTU Hyderabad, JNTU Kakinada, BITS Goa, BITS Pilani Hyderabad, GEC Kozhikode, GEC Gulbarga. This is all about our modules. We have got all 9 modules. You can see basic thermal fluid modules, advanced fluid modules, design and analysis module, transient module, nuclear module, control, electrical and extendability, as well as API module. Okay, thank you. This is all about our Flownex introduction. Next, we will go for our today's case studies. Our first case study is the determination of Stefan Boltzmann constant. First, I will show you what we have taken for this case study. Next, we will show the network, how we have created in our software. First of all, this is some introduction about radiation. Radiation heat transfer is due to emission of electromagnetic waves, which is known as thermal radiation. Heat transfer through radiation takes place in form of electromagnetic waves. First of all, in Stefan Boltzmann constant, we will go for black body. A black body is a body that absorbs all radiation that falls in its surface. Black body is a hypothetical body that completely absorb all wavelength of thermal radiation incident on it. Such bodies do not reflect light, therefore appear black if their temperature are low enough so as not to self-luminous. Next, some theories related to it. Stefan Boltzmann's law, you can see here. Q equals to sigma A T to the power 4, where T is the absolute temperature, A is the area in meter square, sigma is the Stefan Boltzmann constant, which we are going to calculate in this case study, whose value is approximately 5.67 into 10 to the power minus 8 watt per meter square Kelvin 4. This E or Q is the emissive power of the black body. Next, this you can see our problem statement. In this case study, we are going to show a flame temperature of 1250 degrees Celsius. A radiation heat transfer will take place to transfer the heat from the flame to the flowing water. Here the water flow is taking place at 10 degrees Celsius. You can see here this network will show like this. This is the flow of water. Please mute yourselves. This is the flow of water. You can see this is at 10 kg per second. This is the radiation heat transfer. Heat transfer will take place through radiation heat transfer from this place to this place, so that its temperature will increase from 20 degrees Celsius to 92.643 degree Celsius. This is all our calculation. I will show you later. First of all, I will show how we have created our network. This is the network. First of all, this is the boundary condition. For this, we have used one adiabatic flame. This is nothing but for radiation heat source. We have used this flame, whose temperature is given in this format. You can see 1250 degrees Celsius. Means this temperature of flame is 1250 degrees Celsius. Next, we'll go for surface radiation. You can see this component we have used for surface radiation. Surface radiation element we used in Flownex to model radiation heat transfer between two solids node, or between solid node and a flow node, or between two flow nodes. This heat transfer we have used here for radiation. For this, you can see in our network in left hand side in input window, you can see the form factor F12 we have assigned as 1, and for this heat transfer surface area we have assigned as 10 meter square as mentioned in the problem statement, and surface area here also you can see 10 meter square. Next, water is flowing from this side to this side. You can see so For water inlet, we have assigned pressure as 1.2 bar and temperature as 20 degrees Celsius. And this is the flow resistance. Means flow resistance we used here to model the pressure drop through heat exchanger or valve, pipe, ducts or experimental equipments. It is also used for gas, liquid or two-phase flow. Means this is like a pipe also for measuring pressure drop. We have used here this flow resistance. It also can be used to model components with limited geometrical information to reduce the solving time in complex networks. Here we have assigned flow admittance as, for this flow resistance we have assigned flow admittance as 0.001, means it indicates the opening. Means 0.001 means 1 by 1000 times it is open, means very less it has got opening. Volume we have assigned as 0.1. Same thing here, we have assigned flow resistance for this pipe as 0.001 and volume as 0.2. For this pipe flow we have assigned this outlet for this water flow pressure as 1.1 bar. You can see here. Here you can also change all the units. You can see here Newton meter square, Pascal, kilopascal, megapascal, gigapascal. You can do according to your need. So here we have used bar, so we have assigned 1 bar here. Next we will see how much heat transfer is happening by clicking on solve steady state, and here we will see how the network is solving in steady state. For solving steady state, here I already told you have to click on this button. You can see the for solving steady state. Just click on it. After clicking on it, you can see here 100%, means solver convergence is 100%. It works 22 iteration to solve this network, and solver time is very less. You can see 0.01 second to solve this network. And here you can see how much mass flow is happening through this network as 10 kilojoule per second. For this case study, our aim is to calculate the Stefan Boltzmann constant. So you can see the calculation also and how much Stefan Boltzmann constant we are getting through our network. You can see total amount of heat transfer is measured in Q equals to mCp delta T. For mCp delta T, we have used m as mass flow as 10 kg per second because here mass flow is happening only the 10 kg per second, so we have used that one only. And then Cp is 4.187, this is the standard value. Then delta T, change in temperature, as temperature is happening from 20 degrees Celsius to 90 degrees Celsius. If you click on this node also, you can see the temperature, pressure, static pressure and mass source. Mass source minus 10 kg per second means mass source is going out, and this temperature we are getting as 92.6435 degrees Celsius, and here in the at this node we are getting 20. So difference we will take this minus this. So same thing we have mentioned here as this much. So Q we are getting as 3.04156 megawatt through this calculation. Next, by applying Stefan Boltzmann constant, amount of emissivity of black body equals to sigma T to the power 4 into A. So for this, for Q, we have calculated 3.04. So we have put here 3.04. Next, sigma we need to calculate. For this temperature 4, this temperature is in, we are taking in Kelvin, 1250 plus 273. This we have taken from this flame temperature, because in that flame we have mentioned a temperature as 1250 degrees Celsius. So we have taken here that temperature by addition of 273 for converting it to Kelvin. So by this formula we have got this much 5.6532 into 10 to the power minus 8 watt per meter square Kelvin fourth. Because as we all know, for Stefan Boltzmann constant, the value is 5.67 into 10 to the power minus 8, and we are getting at 5.65. It's almost correct. So through this our Flownex, we are getting result of the flow of the Stefan Boltzmann constant as 5.67, which is almost equals. So this is first case study. Next we'll go for another case study, which is the determination of emissivity of the metallic plate. Here we have to determine the emissivity of the metallic plate, and challenges we have to do is the primary objective of this simulation is to determine the steady state simulation of a system where metallic plate is at high temperature emit radiative heat transfer. Benefits of this case study that it will demonstrate the radiative heat transfer. Solution we'll get from this is we'll simulate the radiative heat transfer, steady state simulation will show, and also we'll get the emissivity, how much emissivity is happening. Next, some theory about this radiation. In our first case study also, we have I have clearly said about radiation. Radiation is heat transfer is always associated with the black body. Then radiative heat energy is measured in Stefan Boltzmann's law. According to this law, radiative heat transfer per unit time from a black body is proportional to the fourth power of the absolute temperature, same which we have used in our first case study. This law will use to measure the amount of radiation from a body by multiplying emissivity, absorptivity, and transmissivity factor. Next, same radiative heat transfer. This is the Stefan Boltzmann's law. Q equals to sigma 8 to the power 4th. Same. So emissivity. This you will calculate from this case study. First of all, emissivity. Emissivity is defined as the emissivity power of the surface divided by emissive power of the black body. For the emissivity, for the black surface is always 1. Emissivity of a perfect white surface is 0. If anywhere emissivity is mentioned as 0.9, that means surface will emit 90% of energy and reflect 10% of energy, as it is written here. The information of emissivity is necessary when one wants to find out heat exchange by radiation. In the design of appliance based on solar energy, the knowledge of emissivity of collector surface and reflecting surface is almost for the constant engineer. Next, we'll see our problem statement. In this case study, we are going to calculate the emissivity power. Here, a metallic plate emits radiation and transfers radiative heat energy to the surrounding. The plate temperature is same. We are mentioning here temperature, which is 1250 degrees Celsius, same as first case study. Here we'll calculate the radiation heat transfer and emissivity, and here area of the plate we are using as 10 meters square. This is the calculation which we have taken, we have performed in this. This is the Flownex network. It will see like this. Next we'll go for how we have created same network we have created here. This is the network. You can see for the metallic plate, I think some network issue. This is the network. For the metallic plate, we have assigned one node here. You can see for that node, we have assigned temperature as 1250 degrees Celsius, and for this metallic plate we need to calculate the emissivity, which is emissive power of the surface divided by emissive power of the black body. In this node, which is represented as metallic plate, for this we have assigned temperature. For assigning of temperature, you need to just click on this boundary condition. After that, you can see all the options not specified, fixed on user total value, fixed on solver value. We need to select fixed on user value, means we are the only user. We need to assign the temperature, and the temperature we are going to assign is 1250 degrees Celsius for this node, means metallic plate temperature. Next thing is we will go for this radiation heat transfer. This radiation heat transfer we are using in this Flownex to model the radiation heat transfer, which may happen between two solid nodes, or between two solid node and a flow node, or between two flow nodes. Here we are heat transfer is happening between one metallic plate and a flowing liquid. So we have assigned here heat transfer, radiative heat transfer. For this heat transfer, we have assigned all the inputs. You can see whatever assigned in the problem statement. The plate area we have to take as 10 meters square. So we are taking this plate temperature as plate area as 10 meters square. Emissivity we are taking 0.8 here, and the next for the downstream we are taking surface area same 10 meters square and emissivity as 0.8. Next same which I have already told you for the case study 1, same for this water flow we have assigned pressure or temperature 1.2 bar and 25 degrees Celsius, and this is the flow resistance. We are using flow resistance for pressure drop calculation through heat exchanger or pipe or ducts. In pipe and ducts also we can use flow resistance for pressure drop calculation. All the results after simulation you can see here by clicking on result tab. You can see all the results like mean pressure, total temperature, static pressure, quality, pressure drop, and all the things, velocity also. You can see all the things you can get from the result win tab. Next same flow resistance we have used for the flow. Next for the outlet we have assigned pressure as 1 bar, means from 1.2 bar it will go for 1 bar. Next, for solving this network we have to click on this solve steady state for steady state simulation. So just click on it. You can see here it is 100% solved, means solver time is 0.01 seconds, very less, and it iterates only 17 iteration method. So next we will calculate the emissivity. So we'll go for the presentation here. You can see for radiation heat transfer for black body we have used this formula, Q equals to sigma A emissivity and T to the power 4th, which is the temperature difference. So for sigma we have to assign 5.67 into 10 to the power 8. For emissivity of black body we have considered 1. Then A, area of the plate is already there in the problem statement, 10 meters square. Same we have assigned 10. Then next temperature difference 4th. We have assigned 1200 this much 1250. So by adding 273 we are getting this much, so 1523 to the power 4th. By this formula we are getting emissivity as this much 581.781 watt. And for the surface, this is for the black body. For the surface, same formula we have to apply, and for emissivity for black body is 1, and for the surface we have taken 0.8. Means you can see in the network also emissivity we have taken 0.8. Means for the surface we have taken emissivity 0.8, and for by that formula we are getting emissivity of the surface is 2440465.425 watt by using the emissivity as 0.8. So by dividing emissivity of the black body and emissivity of the surface, emissivity of the surface divided by emissivity of the black body, we are getting emissivity as 0.8, which we have assigned in our network, 0.8. This is for the emissivity calculation. Next we will go for heat transfer coefficient calculation for forced convection. Let me open my forced convection. For this we need to calculate the heat transfer coefficient in forced convection. Here in this case study we will demonstrate the forced convection heat transfer phenomenon in steady state simulation was performed with specific operational input, and all the inputs will be assigned there in the problem statement. In the challenges, the primary objective of this simulation is to determine the steady state simulation of the system where air is flow through a pipe. The forced convective heat transfer coefficient is to be calculated. Means H we need to calculate here, and here we have assigned one heat source which is heat input, means heat flux in a pipe to identify the heat input in the surface. Benefits of this case study that it will demonstrate the forced convection heat transfer phenomenon, and solution we will get from here. It will simulate the flow network, and first steady state simulation was done, and the result of this simulation are as problem statement. Next we will go for the forced convection. First of all, what is forced convection? It is a special type of heat transfer in which fluids are forced to move in order to increase the heat transfer. Means fluid will move by force by using fan or any blower to increase its heat transfer. This forcing can be done in with a ceiling fan or a pump or a suction device. Mechanism of forced convection. The convection heat transfer is complicated since it involves fluid motion as well as heat conduction. The fluid motion enhances heat transfer. The higher the heat transfer rate, the rate of convection heat transfer is expressed in Newton's law of cooling. You can see here Newton's law of cooling. Heat transfer is denoted as HA delta T, and heat flux Q. Heat flux is per unit area, so which is equal to H in H A delta T. Here A is 1. For this, capital Q is the heat transfer rate, H is the heat transfer coefficient which you need to calculate in this case study. A is the area, surface area in meter square. Ts is the surface temperature, this first term, and this T infinity is the ambient temperature. This small q is the heat flux. Next, some examples of the forced convection. This is the example like ceiling fan and normal fan. Next, the ducts you can see in this page. Ducts are the conduits or passages used in heating, ventilation, and air conditioning in HVAC to deliver or remove air. The needed airflow includes, for example, supply of air, return air. You can use ducts in many applications, and in ducts only forced convection is happening, and which will perform in this problem statement or in this case study. Mechanical ventilation uses fan to induce flow of air into or through a building. Ducts configuration and assembly affect airflow rates through the system. Dampers, valves, joints, and other geometrical or material changes within the ducts can lead to flow losses. Next page is our problem statement. For this, we are taking airflow through a duct of 2 meter length and 0.1 meter diameter. Means duct length is 2 meter and 0.1 meter diameter. Then a fan is used to carry the air from inlet to outlet. Means for performing for forced convection, here we have used a blower or fan to carry the air. A heat source is used to heat the air throughout the length of the duct. Means a heat flux, means a constant heat flux we are using in one place to heat the duct. And here we need to calculate the heat transfer coefficient, which is H. And for the air inlet we are using parameters as for pressure we are using 100 kilopascal and temperature as 25 degrees Celsius. And for air outlet we are using pressure as 110 kilopascal and heat source we are using 0.3 kilopascal. Next, our Flownex model. This is the simple model. You can see this is the duct, this is the blower, this is the place where we are using heat input. Next, I will show you our Flownex network. This is our network. You can see for the air inlet pressure and temperature we are assigned here. Pressure as 100 kilopascal and temperature as 25 degrees Celsius as mentioned in our problem statement. Pressure as 100 kilopascal and temperature as 25. For air outlet we have assigned pressure as 110 kilopascal. You can see in the network for air outlet, this is the outlet, so here you will see the how much pressure we have assigned here. For this we have assigned pressure as 110 kilopascal. Next, this is the duct. You can see for the duct you can see all the inputs like with length. Duct length is mentioned in power problem statement as 2 meter. And next,
excuse me, Hitesh sir, just 1 minute.
yes,
I think some people are having problem. So it's a request to participant, please rejoin again the meeting. If you have any issue, rejoin again the event. Okay, Hitesh sir, please continue.
okay, thank you. This is the duct we are using where we will show the forced convection. For the duct we have assigned length as 2 meter by specify length in the profile option. You can assign length. Next, we'll go for the diameter. Diameter for the duct we have taken as 0.1. Increment 1 means it will solve the pipe in one section only. If increment is 10 is assigned here, means it will solve the pipe in 10 segments. Means first pressure drop will be calculated in 10 sections. Next, roughness we have assigned as 45 micrometer. Next, we'll go for our blower, which is helping in our forced convection. For this blower we have taken this fan and pump from this component library. For component you can see here component, all the components is shown here. Whatever components you need to see, you can just type here, like fan and pump. You can see by writing anything, you can see all the components here, fan and pump. Just you need to click on it, just drag into your canvas. This is very shorten your time for simulation. So next I will show you what is the inputs we have assigned. What are the inputs I have assigned for this blower? For this blower or fan, I have assigned efficiency as 1, means efficiency of this boiler is 100%. 1 means 100%, 0 means efficiency is 0. For next thing is our second pipe. Second, in this pipe we have assigned roughness as 45. You can see. Next, heat input. Heat input means here we are giving a constant heat flux which is 0.3 kilowatt. Next, same thing we have assigned here as length as 2 meter and diameter as 0.1 meter. Means the length of the pipe is 2 meter as we have specified in our problem statement. Sorry. Length is 2 meter and diameter is 0.1 meter. So next we will try to solve this network. For solving of this, before that I will show you what are the curves we have assigned here. You can see here fan and pump curve. For the duct we have assigned one curve. You can see, just clicking on it, you can see the duct blower curve we have assigned. By right clicking on it, just click on edit. After clicking on edit, you can see this page. This is the curve we have assigned in this blower. This is the volume flow rate versus pressure. Pressure rise in this axis and volume flow rate is in this axis. For same as NPSH also, net positive suction head. Means volume flow rate versus net positive suction head. We have assigned another curve. You can see here. So this is all about our network modeling. For network modeling, next we will solve this network to calculate the heat transfer coefficient. For that we need to click on solve steady state for steady state simulation. Or solve, after clicking on solve steady state, you can see this solver time is 0.13 second, and iteration it takes 17 iteration to solve this network. Next we'll see the calculation, means how much heat transfer coefficient, means H, we are getting from this simulation. So for that I need to open this one. I have to go for solution. Here we are using Newton's law of cooling, which is nothing but Q equals to HA delta T. Q we are specifying as 300, means here here you can see the heat input we have assigned as 0.3 kilowatt, means 300 watt, which same thing we have applied here as 300 watt. And H we need to calculate here. For area we have assigned pi dl, pi, the value of pi is 3.14, d is 0.1, same thing 0.1, diameter and length is 2 meter, same thing we have applied here, diameter and length. And temperature difference we have taken 46.69 and 40. This is the place here. I will show you. Means after heat addition, means heat input is happening here, so we need to calculate the difference between this outlet and this inlet, because after blower forced convection is happening and it is entering into this duct. So here input temperature, you can see, just you can see here temperature is 40.0684 degrees Celsius, and here outlet temperature is 46.6989. Just you need to click on it. By clicking on it, you can go to result tab. In the result tab you can see the total temperature as 46.6989 degrees Celsius. Here also same thing you can see in the result. In the result you can see the temperature is 40, means this difference of temperature we need to take in the problem statement. So these 46 and 40 we have taken in the from that place only, and we have calculated successfully the heat transfer coefficient by Newton's law as 72.0471 watt per meter square Kelvin. So the objective of this case study is to calculate the heat transfer coefficient for forced convection, which we have calculated successfully. Next we will go for another case study that I will show you directly in the directly in the network only, because in this problem statement we are calculating LMTD, lean mean temperature difference. As you all know what is lean mean temperature difference. We are calculating this lean mean temperature difference for both two types of heat transfer. I will show you. This is the parallel flow heat transfer. First we will calculate for parallel flow heat transfer. Next we will go for counter flow heat exchanger. Per parallel flow heat exchanger, you can see heat transfer is happening between higher temperature to lower temperature. For first line, you can see this is parallel flow heat exchanger, because flow is happening in one direction. This is flow is happening in this direction to this direction. Same for this direction to this direction. So here we will calculate the lean mean temperature difference for this parallel flow. This is the hot fluid side, this is the cold fluid side. For the hot fluid side, we are assigning, you can see, we are assigning pressure temperature for hot side as pressure as 1.2 bar and temperature as 80 degrees Celsius. And this is the hot side outlet, and we are getting a mass source of minus 1.35 kg per second, means 1.35 kg per second mass flow is happening, it's flowing from this place to this place. And this side is for cold fluid. This is the cold inlet side. For the cold inlet side, we have assigned temperature as 30 degrees Celsius and pressure as 1.2 bar. For the cold side, same mass source we are considering here as minus 1.3. Minus means to here mass flow is happening from this side to this side. Next, I will show you about the heat transfer phenomenon. For this, let me largen my system. First of all, this is the composite heat transfer. Composite heat transfer you can see in the identifier. Identifier means the unique name for this component. You can see identifier. Composite heat transfer. This composite heat transfer we are using to show both conduction as well as convection in upstream as well as downstream. As heat transfer is happening from hot side to cold side, first of all, from for heating the pipe surface, means for heating the pipe surface, for first convection will happen. For the metal which are present in the pipe, for that heat transfer, for then conduction will happen. Then for the whatever flow is happening inside the pipe, that heat transfer is again convection. Same thing we have clearly assigned here. You can see, first of all, for the conduction, we use overall heat fraction as no. Conduction heat area we have taken as upstream area as 33.9, means upstream is this one, downstream is this one. For this upstream pipe area, we have assigned 33.9 meters square. Next, for that pipe, we have assigned thickness in element direction. Thickness in element direction means 2.5 mm we have assigned here. Thickness in element direction means the pipe thickness. This pipe thickness means thickness of the pipe as 2.5 mm. Thickness in cross direction. Thickness in cross direction means length of the pipe. Length of the pipe we have assigned here as 3. Number of node means 2. Here at 2 points heat transfer we are calculating. Next area, downstream surface, mean downstream area surface we are assigning as 32.2 meters square. Next we'll go for, you can see, convection upstream. Convection upstream, here simple heat transfer option we have assigned as convection, because convection heat transfer is happening to heat the pipe wall. For that convection coefficient we have assigned as calculated h, means it will automatically calculate the how much h is there. So if you click on constant h, you can see if you have data related to heat transfer coefficient, you can assign here. For that we need to specify here heat transfer coefficient as constant h. Here we don't know how much exact h is there, so here we have assigned calculated h. Fin efficiency for the upstream is 1, means 100%, and all these inputs are by default. We no need to assign here. For the downstream, same we have assigned heat transfer as convection, and convection coefficient option as calculated h, means it will automatically calculated how much h is there. So fin efficiency is here also 1, means 100%, and roughness we are taking here as 45 micrometer. Next, I will show you how we have calculated LMTD for this parallel flow. For that, we have assigned this script. Script is for addition of all the formula, means whatever formula is there, you can easily add by using C# language. Just double click on it to see all the parameters which are there in the script. Let it open. I'll show. You can see here wait 1 minute. Here in the pipe number of increment here is we are taking as 10, means it will divide the pipe in 10 segment to solve this. So we have length as 3, so it will divide the parts in equal 10 parts. As you can see here, LMTD, for calculation LMTD we have assigned from 0 to 0.3.8 and it is going for 3, means last option is 3. Here we have assigned LMTD for CF, means CF means counter flow, LMTD for PF means parallel flow. As we know, for the LMTD formula is the difference between inlet side and outlet side. I will show you the formula for LMTD for parallel flow. This is THI minus TCI. THI means hotter side inlet minus colder side inlet divided by a minus temperature of hotter side and the difference between the hotter side temperature, then logarithmic of this difference. So we have assigned same formula in this script. You can see here this formula, you can see, and we are calculating LMTD as 83. Before that, I will show you the counter flow part. For counter flow part, heat transfer direction is opposite. For first hotter side, heat transfer is flow is happening in this this side, and for this colder side, heat transfer is happening in this side. So for the hot side inlet pressure and temperature we have assigned as 1.2 bar and 80 degrees Celsius, and for the mass source we are taking same 1.35, and for the cold side we are taking pressure as 1.2 bar and temperature as 30 degrees Celsius, and mass source same minus 1.3, means mass flow is happening from this side to this side. Is mass flow is mass source is entering to this node. So for this heat transfer, same composite heat transfer we have used here. For I have already explained how composite heat transfer works. It works both for both heat transfer, for specifying for adding all the information related to conduction as well as convection, as 3 types of heat transfer is happening here. I mean, 3 phase here heat transfer is happening first convection, then in pipe metal it is conduction, then inside the pipe for heating the flow, heating the fluid, it is again convection. So same thing we have assigned here. You can see for upstream surface area 33.9, and for element direction, then cross direction means length of the pipe. Here one thing I forgot to tell you all, that here we are using material as stainless steel 316. You can change your materials also. All the materials which are there in for the pipes is assigned here. Here we are using metals, so all the here also you can see all types of material is there in the master database. So next, same thing we have assigned here for this script. Just double click on it, you can see all the formula which are we have assigned through C# language. As increment is number of increment of the pipe is 10 and the length of the pipe is 3, so it will divide the pipe in 10 segment. By dividing equal parts, we are getting 0.3 difference between each segment. So for the first we have taken 0.3, and accordingly it goes. Next, let me zoom out to show the curve also. For this counter flow, if you see the counter flow curve, it will be like this only. This is the hotter side inlet, this is the colder side hotter side outlet, this is the colder side inlet, this is the colder side outlet. Same thing for counter flow LMTD calculation, parallel flow. This is the hot side inlet, hot fluid inlet, this is the hot side outlet, this is the cold side inlet and cold side outlet. You can see here, as we in this pipe we have assigned number of increment as 10, so it is divides the pipe in 10 equal length. You can see 1 2 3 4 5 6 7 8 9 10, means this difference is 0.3 only. Here you can see 1.53 0.15 meter, here 0.45, next it is keep on adding 0.3. This is the curve between total temperature and length, because for calculation of LMTD we have introduced this curve to show you clearly how LMTD is calculated through this formula. Let me zoom it. This is for the parallel flow LMTD calculation. This is THI, TCI means this is the THI. Sorry, THI minus TCI means THI is this one, THI is this one, and TCI is this one, means colder temperature. Then THO minus TCO. THO is this one, TCO is this one. Divided by logarithmic of this difference, divide of this difference. Same we have calculated. So before that, I will show you how we solve by clicking on solve steady state, how much LMTD we are getting here. So for that, just click on solve steady state. By clicking on solve steady state, you can see here solver time is very less. It is less than 1 second also, 0.58 second, and iteration it is taking for solving this is 37 iteration is taking. So LMTD here we are getting it as 38.199, and for this is for the parallel flow, and for the counter flow we are getting LMTD as 38.995. This is all about our this case study. Next we will go for vapor compression refrigeration system. Refrigeration cycle will go. So see the vapor compression. So let me show you all our case study PPT, this one. Here in this case study, we'll demonstrate the modeling of vapor compression refrigeration system using R22 refrigerant. Here we will show you the simulation in steady state as well as transient. Challenges we need to perform here is that will determine the steady state performance of the system given the design of all the component together with appropriate boundary condition. Whatever components are used in vapor compression refrigeration system will show you here. And benefits of this case study is that we'll model the vapor compression refrigeration system using R22 refrigerant. So solution here in solution we'll simulate the vapor compression refrigeration system. Next the theory part. This is the vapor compression refrigeration cycle. Cycle will start from this side. This is the first cycle, first phase, first process. This is adiabatic compression, which is happening in compressor, where there is no heat flow. Next here, this is the condenser part. For condenser, this here heat will be rejected at constant pressure. And then 3 to this one 3 to 4 is isoenthalpic expansion, which will happen in capillary tube or expansion valve. Next evaporator. In evaporator, heat will be added at constant pressure. So this is the cycle. This is the simulation, means what are the devices are there in this cycle, for starting from positive displacement compressor, condenser, expansion valve, and evaporator. This is all about our inputs, and our cycle will look like this one. This is the steady state result, and all about curves. Okay, I will show you how we have modeled this one. This is the complete vapor refrigeration cycle. Evaporation cycle. This also you can use to model the heat pump also. Same network with for calculation COP. Here we have calculated COP for both refrigerator as well as heat pump. First process is adiabatic compression. This is the first process from this place to this place. In this node, we have assigned for this compressor input, we have assigned pressure and temperature as 400 kilopascal and the temperature as 5 degrees Celsius. In this node, means inlet of this compressor is this much. So for this compressor, we have mentioned all the inputs for the compressor. For this compressor, we have added speed of the compressor as 2600 rpm, swept volume as 0.01 meter cube, and dead to swept volume as 0.1. Number of stages in the compressor we have assigned as 1. And efficiency, you can see efficiency option, isoentropy efficiency we are selecting. You can select also other efficiencies. Isoentropy efficiency we are mentioning as 0.9, means 90%. For this, in this adiabatic expansion, there is no heat flow. Next, our process is for condenser. For condenser, heat will be rejected at constant pressure, means how much pressure is there at input, output, same pressure I will show after simulation. For this condenser, we have used same composite heat transfer. For composite heat transfer, you can see conduction as well as convection we have assigned here. For conduction, you can see here in conduction also layer option is there. In layer, if you double click on it, you can see the layer. In that layer, you can assign all the pipe properties here. In that pipe properties, you can see thickness in element direction of the pipe means thickness of the pipe. Element direction means pipe thickness. Thickness in cross direction means 3. Here length of the pipe is 3, and the number of node is 2, means node in heat transfer direction is 2. Area in downstream mean downstream surface area we are assigning as downstream surface area we are assigning as 25.5 degrees Celsius. Here we are assigning material as copper, cartridge brass, which is a metal also. All the conduction related inputs you can assign through layer option. So this is all about layer. This is the as heat transfer is happening between the here to here. This is condenser. So heat rejection will be there at constant pressure. For heat transfer, this is one type of fluid is flowing this in this circuit, and here one fluid is flowing. So heat transfer happening from this side to this side. For this side, you can see we have assigned for the flow we have assigned pressure as 120 kilopascal, temperature as 6 degrees Celsius. For this input, for outlet boundary condition, we have assigned pressure as 110 kilopascal. So due to pressure difference, flow will happen. This is the same flow resistance which we have used for the pressure drop calculation. This can be used in heat exchanger also, pipe, ducts, and other experimental equipments to calculate the heat pressure drop. You can see in the result tab also pressure drop. You can see from here the pressure drop, and it can be used in for gas, liquid, and two-phase flow. Here we are using. You can see the just click on any component, right click on it. You can see one assign fluid. Here you can assign what are the fluid you can use. You just click on it. You can see as the refrigerant is flowing in this path, so we are using R22 refrigerant, which is two-phase flow. You can see two-phase flow, refrigerant, then R22. R22 we have selected. This is the R22. After that, you can click on OK. So everywhere that same fluid will be assigned, R22 fluid. This fluid is already there in the master database. I'll show you. The component tab. This is the component tab. Let me enlarge it. The component tab. You can see all the components like containers. Containers means accumulator, all types of accumulator, reservoir, two-phase tank, vented container, two-phase tank. If two types of flow is happening, water and steam is mixing in one place, so you can assign this one. Reservoir, for any fluid you can use reservoir. Custom losses for pressure drop calculation, you can use custom losses. For custom losses, so many types of components are there. Here we are using same flow resistance, general empirical relation, lumped model, all secondary types of losses we can assign, and all types of flow meters also is there. You can see all types of nozzle, 3-degree nozzle, 7-degree nozzle, dull tube differential flow meter, and nozzle differential flow meter, orifice differential flow meter. All types are there. This is the nozzles, discharge nozzle. For exit thrust nozzle, you can use this one. For normal nozzle, you can use this one. For all types of ducting also, facilities are there. Where cross junction is there, you can use damper, ducts. This I am showing you because you can know all our capabilities. Means for flow parameters, you can use this tool very effectively for piping design, This is
Hitesh sir, sorry for disturbing you. There is one question in the chat box from the Abhijit Datta sir. Please look into it.
okay. Can I explain this latter stage, or I will explain now?
Okay. Abhijit sir, we will answer your question in the end of the session, sir.
And this.
Hitesh sir, you can continue.
Maybe
See.
essential or
Abhijit Datta. Yeah. Okay, I will answer this afterwards.
this all will
Okay,
be
sir.
available.
This is all about heat exchanger. As today's discussion, we are more focusing on heat exchangers. So you can see all types of heat exchangers are there here. For bulk air cooler, you can use this one. For cooling towers, which are there in power plants, for natural and forced flow. So this is cooling tower, evaporator. All types of heat exchanger like fin tube heat exchanger, fin side, fin tube heat exchanger, tube side, and then heat exchanger primary, secondary. Means various types of heat exchangers are there. For cell and tube type heat exchanger also there. For heat transfer also, so many for transferring heat. This is the component we have used in our networks. This is composite heat transfer. For solely for conduction also, heat transfer is there. Convection also, cross conduction also, film convection, fluid radiation, jet impeachment convection, then surface radiation. All types of things are there. Related to pipings also, you can see all types of pipes also there. Basic pipe, bend. If you are more focusing about bends like 45-degree bend, 90-degree bend in flow path, you can use this bend insulated pipes. This is normal pipe. This is the restrictor. Restrictor means types of valve. Restrictor with discharge coefficient, we can assign your discharge coefficient through this valve. This is the loss coefficient. Loss of coefficient you can assign here. This is all about the component, and you can see here also all types of pumps and turbos. You can see compressor stages. If various stages are there in the compressor, you can assign here. Fan and pump, positive displacement compressor, simple turbine, simple to complex turbines. Like if 3 stages are there, you can assign also turbines, variable speed pump, and steam turbines also. Various types of valves also are there, like all types of control valves, basic valve, check valve, control valves with loss coefficient, excess flow valve, and the pressure. So this is all about components. If you want to see all the charts also, this is a chart and lookup table. In charts and lookup table, you can assign your own charts here. This is all about components. Next we'll go for this network. This is for all about this condenser, where heat rejection is happening at constant pressure. Next we'll go for isoenthalpic expansion, which we are using here. Restrictor with loss coefficient as capillary tubes or expansion valve. For this as here expansion of we are expanding subcooled liquid at constant enthalpy. As a result of expanding of subcooled liquid, here internal energy will be reduced. By when internal energy will be reduced, temperature also reduced. Here you can see we have used for this isoenthalpic expansion, we have used restrictor with discharge coefficient, and all the inputs related to this expansion valve. You can see here for that cross sectional option we have assigned as diameter, because here opening we are specifying as diameter. Here you can specify area also. As diameter option is there, you can mention or write your own diameter as 0.05 meter, and discharge coefficient is 0.7, means it's 70% open. Next, parallel means only one tube, one flow path is there, so number of parallel is 1, opening is this one. And next, this is the isoenthalpic expansion outlet node. I will solve this network. Next, I will show you this stage. This stage is heat rejection at constant pressure, which is evaporator. For the evaporator, heat transfer is happening from this side to this side, means heat transfer direction is this side. So for that, here you can see fluid is pure fluid, gases, air. So between R22 refrigerant and gases, heat transfer is happening. And how much heat transfer is happening, you can see here 39.469 kilowatt. In this experiment also, we have calculated the COP, coefficient of performance, for this refrigerator. So for this is the evaporator side. For that evaporator side, for this gas flow inlet condition, we have assigned pressure as 101.325 kilopascal and temperature as 6 degrees Celsius. Next, this for this gas outlet is pressure is 100, means this is flowing from 0.101 to 100 pressure. And this is the same for pressure drop calculation. Means for flow phenomenon, we have used this flow resistance. This is the most convenience used to denote to represent our heat transfer. As here both type of heat transfer you can assign here. Same I have explained earlier, composite heat transfer. For that composite heat transfer, this layer part I have explained to you earlier. Same thing for the this is the element direction thickness, this is the cross direction thickness, 10 meter. Next, for the convection in upstream and downstream, here we have data related to heat transfer coefficient. So for the upstream heat transfer coefficient, we have assigned here as 700 watt per meter square Kelvin. The units you can see here, all types of units is there. So fouling factor is we have assigning as 0, and fin efficiency as 1. Is fin efficiency 1 means it's 100% efficient, means it's working 100% for upstream. Downstream, for the downstream heat transfer option is also same, which is convection. And for that convection coefficient, we have assigning here as 8560 watt per meter square Kelvin. So fin efficiency is here as also we have assigned here as 1. So this is the full network. I have explained how we have created this network. Next we will go for solving this network, and we will calculate how much is the coefficient of performance. Please please give me 1 minute. Welcome.
As the faculty training
Participants, if you have any questions and if you have any doubts, you can ask us in the chat box. You can simply type your questions and the queries in the chat box, and we will answer you in next few minutes.
Sorry for the interruption. Okay, let me show you the network again. This we are discussing. I have successfully explained all about this vapor compression refrigeration cycle, all the 4 processes, which are adiabatic compression, heat rejection at constant pressure, then isoenthalpic expansion, then heat rejection at constant pressure. Next, we'll go for this steady state simulation. For that steady state simulation, same, we have to click on this tab, solve steady state. You can see this is 100% solved. So next thing is for us to calculate the COP of this cycle. For this COP, you can see here COP of the refrigerant we are getting at 0.1. For that, we have same thing we have added for representing our formula for COP in script. Let it open. I'll explain. This is one. You can see here for calculation of COP for a refrigerator as well as heat pump, we have written one C# code here. This is COP for refrigerator values. This is COP for heat pump. HP means heat pump. This is the heat low value divided by work input. So it means COP of the refrigerator we are calculating by dividing heat transfer which are happening in the evaporator, which is heat low value divided by work input, means how much work is work done is happening in this means this sorry means heat COP of the refrigerator is how much heat transfer is happening in this place, which is represented in this composite heat transfer result. You can see convection conduction heat transfer 39.4686, as well as convection heat transfer is also same. This is the heat transfer which is happening. COP of the heat transfer will calculate it by dividing this value with this compressor work value. So compressor, for compressor also same result tab. You can see the power of the compression. Power is consumed here, so here negative sign is there. So for calculation of this COP, we'll divide these two value to calculate the COP. Same thing we have added in this script. So this is the script we have added. For introduction of script, all the inputs you can assign here by writing here only in the display name. What is the name you want to display here, like heat low value, which is the evaporated heat transfer value, high heat value, which is condenser heat transfer value. This is the work consumed, which is happening in the means displace expand this displace adiabatic compression in compressor, that value we are assigning here for work consumed. Then same thing COP we are going to calculate it here. For this COP refrigeration values, we are calculating by dividing this evaporator heat transfer value with the compressor work input. For the heat pump, it is just we need to divide this high heat value. High heat value means this high heat value means this value which is happening in this condenser 254.684 kilopascal. 254.684 kilopascal you can see in the result tab. In result tab you can see conduction and convection heat transfer in kilowatt. This for heat pump we need to divide this value with this value. So same thing we have as we have represented in our script as COP of the refrigerator and COP of the heat pump. As we all know, COP of the heat pump is equals to 1 plus COP of the refrigerant. So we are getting here COP of the refrigerator as 0.181 and so as the COP of the heat pump as 1.170. So this is all about this vapor compression refrigeration system. Here for vapor compression refrigeration system, we have calculated the COP of the refrigerator. This is the heat transfer. Here V option, you can, if I zoom it, you can see view option. View option is nothing but if you right click on it, go for view, you can see from where it is taken. Means if you need to copy the all the value of this heat transfer, you just need to click on view. View means it will go to means assign same value if you copy it in another place. So this heat transfer value we need to assign in this script. So we have applied view. Same this heat transfer is which is used in this evaporator. If you right click on it and click on view, you can go to this one. So this is for same thing here also. If you go click on view and go to this one, then you can go for this one. Then this is the through data transfer link. This is for transferring data from this heat transfer to the script. If you click on it, just right click on stream heat transfer values to the script high heat values. Same goes for this one. If you click on it, go for detailed property association, you can see upstream convection heat transfer. We are taking it to the same heat low value, which is happening in evaporator. Same for the compressor. For compressor, same thing. We are adding, introducing this total power of the compressor to the script W inlet. So as work is consumed here. So same thing we have added here. So as in condenser, this is the condenser side. As in condenser, heat will be rejected at constant pressure. So pressure you can see in this node. If you go to this node result tab, pressure is this one, 2925.24. Same thing, which same pressure is there at the outlet also, 2925.23 kilopascal, means heat is rejected at constant pressure. How much heat is rejected? This much heat is rejecting, 254.684 heat. Same. Then same thing for evaporator also. By after solving this for steady state, then you can check for the pressure also. In the pressure you can see for the inlet pressure is 400 kilopascal and for the outlet also 400, means here also heat is added to the system at constant pressure. And you can see here for this cycle also 3 to 4, which is isothalpic expansion, where we will expand the subcooled liquid at constant enthalpy so that its internal energy as well as temperature will be reduced. So you can see temperature at the inlet, you can see total temperature is 68.81 degrees Celsius, and here you can see the temperature as minus 6.55, means temperature is reducing so much, so that you can use this is in refrigerator. So this is all about this cycle. It's all about our case studies. Those who have any doubt, they can ask in chat box or comment box. Those who have any doubt, this is all from my side. You can ask any question.
Yes, participants, you can ask the questions to the Hitesh sir. You can write down your questions in the chat box, or you can simply unmute yourself and you can ask direct questions to the sir.
One of my colleagues is also there. Ayush is my colleague also.
Hitesh sir, request, first you answer the chat box questions.
I think, sir, I think Ayush has answered all the questions. You can check also. Siddhartha Baumik has questioned me, like could not keep continuity due to networks disruption. I think he needs good network. And others asking about feedback link. That is not my concern. And all other questions, I think Ayush has answered. Any chance of getting Flownex student version? No, there is no facility. I think you can contact IndiaSoft also.
Yes, and there is a COP refrigerator realistic. I think
Yes.
I answered also that question.
Uh-huh.
Okay, participant, did you have any other questions you want to ask yourself? You can ask in the chat box, or you can please ask in by unmute yourself, and you can ask directly to the Hitesh sir. Sir, Hitesh sir.
Yes.
Please answer for the Abhijit Datta question. It is timing is 15:42. Yes, this one 42.
Abhijit Datta has a question like, if heat source is flowing, also flowing, is it possible to simulate in the flow software Flownex? Another important question is there, if there is a branch flow, how to determine the single branch flow characteristic? Yes, easily you can show all types of branches. Branches you can go for I'll show you. Like this is one flow is happening. If you go for another branch, like we are introducing pipe in another parts, just click on it, just for upstream node, just add it, and for this click another pipe and mention one boundary condition. It's very easy. Yes, you can do that one only. And boundary condition you can assign here. For the pipe, all the inputs you can assign, like length. It is not realistic data. If you have specific problem, Abhijit sir, if you have specific problem, you can ping us. You can contact IndiaSoft also. They can give our number, contact number. We can solve that. Yes, it is easily possible. 3 meter.
And just Abhijit sir, one more question was that if heat source is also flowing, is it possible to simulate that? Let me clear, Abhijit sir, this is a 1D simulation software. Like for example, if you want to see a flow which is in the 3D, is not possible here. You will have to use other tool which simulates a 3D. But that's a source simulation. Only a part simulation will be done. This is a complete circuit as well as whole cycle simulation we are doing here. So no specific source related simulation or any specific geometry related simulation will not be done here, because it is a one-dimensional simulation. So that is the answer for you. If you have any doubt or any questions, then please go ahead.
And related to software, you can ask to IndiaSoft.
And everyone please submit the feedback form. Okay, so feedback link is provided in the chat box. So according to that feedback link, you will get certificate only.
And if you have any queries now, you can now directly unmute yourself and ask us the questions.
Yeah. is also posted in the chat box. You can submit the feedback, ask question in the feedback also. We'll get back to you. And without feedback, you will not get certificates. So feedback as the name you required and details you required should be submitted.
And I would like to thank you, participants. From last 2 hours, they are with us, especially for the VT colleges and all the colleges from the Northeast also. Okay, so thank you very much. And we will bring up the new sessions
Feedback
next in the next time.
Kazi sir has asked, please provide in the WhatsApp. Sir, feedback link is not provided, will not be provided in the WhatsApp, because those who, like you can see, 75 participants are only attended, and in the group there are hundreds of participants. So those who have attended, they will only get feedback. So that's why we have pasted that link in the chat box only. So please the chat box and submit the feedback from that link. Copy that link and paste it in your URL and submit feedback.
Any questions, participants?
May I ask a question, please?
Yes, Roy sir, please.
In the month of August, I attended one webinar organized by you. It was on virtual CNC.
Yes, sir.
Okay.
I'm yet to get the certificate for that.
Okay, sir. I'll check back to that because they had already sent the certificate mail. But if you haven't got that, we'll get back to you. Don't worry. Yeah. Any other question? So, if anyone has a question, if you're feeling a feedback or something, we are giving a 2 minutes for the last question and answer session. After that, we will conclude our session. So, feed the feedback also, and 2 minutes for the question and answer. We will take 2 minutes more for the question and answer. So if anyone has, he can type that question answer in the chat box, or he can
Itself, and you can directly ask questions to us.
Any question, participants? Then please go ahead and fill your feedback, which is in the chat box.